Hi everyone, in this video we are going to cover section 6.4, arc length of a curve and surface area. The first part of the section deals with arc length. All right, so our goal in this first part of the section is to measure the length of a curve. It's easy to measure straight lines. It's challenging to measure curvy lines using math, right? We could use a string, of course. That wouldn't be that challenging, and bend it along the curve and then pull it tight and measure how long that string is. But that's not that interesting. But in calculus, we measure the length of a curve by dividing it up into a bunch of shorter distances and subintervals. And then ultimately, when we take the integral, that takes the limit as n approaches infinity. So we get a lot of really, really thin, or not thin, a lot of really, really short sections that we add up together. We never actually compute them. Okay, that's called integration, and it saves us all the time of dividing your region into subintervals. Okay, but let's just focus in on one of these subintervals. So I'm going to scroll down and zoom in on that first subinterval. And this is the goal here is to kind of understand where the formula comes from, because it's pretty cool. And in calculus class, oddly enough, something that comes back in a beautiful way is the Pythagorean theorem. All right, and so if I want the length of this distance, right, I want this is our goal here, is we're trying to find the length of this, and that length is an approximation of this length. And you might be thinking to yourself, well, they don't look like that curve is way longer, right? But in practicality, in the calculus, right, this wouldn't be that wide. It would be a really, really short section to get a good approximation. But if my goal is to get the length of this, the hypotenuse of my right triangle, well, I can use the Pythagorean theorem and say, all right, the leg squared plus the leg squared is equal to the hypotenuse squared. And in this, we can see that we have the leg measured as delta x. This leg along the x-axis is delta x. It's some small change in x. That's what delta means. And this leg, the vertical one, is some change in y, delta y and delta x. And so we can approximate this distance here by taking the square root of delta x squared plus delta y squared. That approximates the length of that section of our curve. So now I want to mess around with this square root a little bit and ultimately lead you to the formula. All right, and what I'm going to do is from each of these two terms, I'm going to factor. So I want to write this as delta x, that quantity delta x squared, times something in parentheses. If I take delta x squared out of itself, I'm left with 1. If I take delta x squared out of delta y squared, they have nothing in common, so I just have to write that as plus delta y squared over delta x squared. And that really can be written, well, actually, let me do this first. So I'll come back to this, the end in a second. The first thing I can do is, because I have a square root of a factor now, something times something else, I can take the square root of the first term, the square root of delta x squared, just delta x, times the square root of the other stuff, 1 plus. Now, this ending term here, I want to write that a little differently. The numerator and denominator are both squared. So this is delta y over delta x, that whole thing squared. And what is a change in y over a change in x? A small change in y over a small change in x, other than just the derivative, right? That in parentheses that I'm now circling in blue, that is just f prime of x, f prime of x. So our length is of each little subinterval of each section is found by taking delta x times the square root of 1 plus f prime of x squared. And that, when I scroll down a little bit further, is where the formula comes from. So it's just the Pythagorean theorem, but then we messed around with it so we can infuse our calculus terms. And so when I scroll down here, to measure the length of an arc, we have the integral from a to b, because that's our interval, of the square root of 1 plus f prime of x squared dx. So in my length up there, the delta x, this translates down in the integral to be the dx. The square root of 1 plus f prime of x, that's exactly what it is. And instead of finding one subinterval, we integrate over our whole region. All right, so that's the formula that we'll use for the beginning of this section. Our first example gives us the function f of x equals 2x to the 3 halves with the arc length of f of x over the interval from 0 to 1. So here's my function, here's my interval, and what I'm going to do first, before I write down my integral formula, I'm going to write down my function, 2x to the 3 halves. I'm going to write down its derivative. The 3 halves comes down to the and times x to the 3 halves minus 1 is 1/2 power. The 2's cancel out, and we're left with 3x to the 1/2 power. Or I could write that as 3 radical x. The other thing I like to do ahead of time, before I get to my integral, is I want to take f prime of x and square it. I think the formula has it in brackets like that. So I'm going to square my derivative. 3 squared is 9. X to the 1/2 squared is x to the first power. Actually, I'll write that out as 2 separate steps. So this is 3x to the 1/2 squared, which is just 9x, as I said before. All right, so that's my preliminary work. Now I'm going to go to my arc length formula, the integral from a to b of the square root of 1 plus f prime of x squared dx. Substituting in the work that we've done so far, we have the integral from 0 to 1, 1 plus 9x dx. There it is. To do this integral, to evaluate this integral, we do need a little u substitution. We'll set u equal to what's under the radical. du is 9 dx. And since I don't have a 9 anywhere else inside of my integral, I need to divide by that. So 1/9 du is equal to dx. Ultimately, that u substitution puts a factor of 1/9 out in front of my integral. Because this is a definite integral, we also need to write our bounds, but let me substitute in what I know first. This is the square root of 1 plus 9x. So I'm going to write that as u to the 1/2 power du. The 1/9 du goes right there, and the u is under the radical, but really we're writing that with a fraction. Now let's look at our bounds. Top bound is 1. 1 plus 9 times 1 is 10. The bottom bound is 0. 1 plus 9 times 0 is 1. So our new bounds, our u bounds, are from 1 to 10. All right, now it should go a little bit more familiar. Oh, there's the next example peeking in. Let's do our antiderivative. 1/9 u, oops, let me write that differently. U to the 3 halves over 3 halves, evaluated from 1 to 10. We'll simplify. 1/9 times the 2/3 comes up. And then let me plug in top bound is 10 to the 3 halves minus 1 to the 3 halves. And now from here, we could simplify it a little bit further. This is 2 over 27. 10 to the 3 halves gets kind of ugly. 1 to the 3 halves, that's just 1. Ultimately, I think I want to write this just in decimal form. So this is one where you would use your calculator. This is equal to, well, actually not equal. It is approximately equal to 2.268 if you check it in your calculator units. So that is the length of the arc, the curve of the function over the interval from 0 to 1. All right, hopefully not terrible. The substitution is really the new thing. In the beginning, the substitution into the formula is the new thing. And then we use, hopefully, now starting to be familiar techniques. All right, in this next example, we'll see how some of these problems can get a little bit challenging. Okay, but when they're challenging, fortunately, since we're only in Calc 1, we do less work. And you'll see what I mean in a minute. In this one, my function is x squared. Right? That's a pretty standard function to work with. It's just a parabola, right? The first one x to the, or is 2x to the 3/2 power. That's not a function we work with on a regular basis. This one is just a parabola. So let's take the derivative now. F prime of x is 2x, and then we square it, and we get 4x to the 2nd power. So substituting into my arc length integral, we have our bounds are 1 to 3, the square root of 1 plus 4x squared dx. And then we stop. And let me explain why. This is one where if I tried to do a u substitution, 1 plus 4x squared du is equal to 8x dx. The 8's not a big deal, but do you see an x anywhere in that integral other than right there that would make this substitution work? The answer is no, there's not. Okay, so since we are quote unquote only in Calc 1, we're done. We can use computer software, so you can use some website to give you the answer. If you check in OpenStax, they tell us that this is 8.2626815. But you do not yet have the techniques, the tools to evaluate this integral. If you have me in Calc 2 or someone else in Calc 2 is fortunate enough to have you as a student, well, then you get to learn about trig substitution. Let me tell you, that is some good stuff. That's what we need to do here, something called trig substitution. It's pretty cool, but we don't have that technique yet. We don't have those skills yet. So even something as standard as a parabola, it gives us a challenging integral to evaluate. All right, so for this one, we'll set it up and look up the answer, call it a day. The other topic that we encounter in this section is that of surface area, or the area of a surface of revolution. All right, and this piggybacks very much off of what we just did with arc length. And so what we are going to do is take this length and revolve it, as we did earlier in Chapter 6, spin it around the x-axis. We revolve around the x-axis, and then we produce this solid shape, but the formula that we're going to see in just a second, it will find, instead of the volume, as we did earlier, of this three-dimensional object, we're going to find the surface area, the area of the outer surface of this mass, of this thing, if you will. Okay, and so because we're taking the actual curve, spinning it around the x-axis, we're going to see the same thing in the formula that we just did with arc length. So down here, right, let me get my pointer, right here, the square root of 1 plus f prime of x squared, that's in the integral. But we also, in front of that, have this 2 times pi times f of x. So what does that represent? Well, 2 pi times f of x, if I pick some point here, x, f of x is really just the height at that point, right? 2 pi times f of x is the radius as I revolve this, that one single cross-section around the x-axis. 2 pi times f of x is that function revolving around it, that circular cross-section revolving around the x-axis. Okay, so that's, if you can kind of picture some little animation of this spinning around, right? Those spin around in circles. 2 pi times the radius is that's what that does in the formula, spins it around the x-axis. Okay, ultimately, we need to be able to set these up, substitute into them, sometimes solve them, and other times we'll only be looking at setting up these formulas. And then, of course, at the bottom here, we have, if we're revolving around the y-axis, everything just needs to be written in terms of y. Let's look at our last example for this section, and our function is the square root function, f of x is equal to x to the 1/2 power. They give me the interval from 1 to 4, and we want the surface area when we revolve it around the x-axis. Okay, so we need lots of things. We need the function, we need its derivative, 1/2 x to the negative 1/2, and then we need to square that derivative. So 1/2 squared is 1/4, and x to the negative 1/2 squared is x to the negative 1, or I could write that as 1/4x. All right, I think we have all of our preliminary work. I want to, since this is our first example, write the formula down again. I'm going to abbreviate surface area. SA is equal to the integral from a to b, 2 pi times my function times 1 plus the square root of 1 plus f prime of x squared dx. All right, that's a hefty integral to substitute everything into. But let's see what we get. Bounds are given, 1 to 4. 2 pi, I can pull that out in the next step, factor it out. 1 over, f of x first, excuse me. That would be x to the 1/2 power times the square root of 1 plus 1 over 4x dx. So that's what it looks like when we have everything substituted into our integral. And I actually want to take and erase one thing and write it a little bit differently. That x to the 1/2 power that I wrote there, I actually want to call that the square root of x, the original function that it was. And the reason for that is, you know how earlier in the section I pulled that square root of x squared out of the radical? Well, now I want to multiply these two square roots together. That's how we're going to simplify this. So we're going to say 2 pi times the integral from 1 to 4, and we'll multiply those two radicals together. This x multiplies by the 1 first under the radical sign, and then that x multiplies by the 1 over 4x. So we have x plus 1/4 dx. And so the way this works out, once it's simplified, this one is a pretty direct u substitution. U is equal to x plus 1/4. Du is equal to dx. And, my bounds, I might as well do them now. 4 plus 1/4, let's say 4.25. And 1 plus 1/4, let's say 1.25 for my two bounds. Let me give myself some more space here. So our surface area is equal to 2 pi times the integral from 1 1/4 to 4 1/4, and then it's u to the 1/2 du. Take my antiderivative, substitute, call it a day. 2 pi. I'm going to flip that denominator right up. It's u to the 3/2 over 3/2, but we know that we're going to get 2/3 u to the 3/2 evaluated over the bounds. It's 4 1/4, 4.25. And then from here on out, it's a calculator question. Top bound minus bottom bound, and you should get 30.846. Alrighty, so that is the end of the section. Did two examples of the first arc length and one example here of surface area. If you have questions as you work through the homework problems, please send me an email. Thank you very much for listening. Have a wonderful day.